Hi then, this is the last lesson of the semester at 6G, weighted graphs and networks, where the learning intention is to be able to find the shortest path on a network. Now, weighted means a network which has got numbers attached to it, as in this case here. So we don't just have a network of towns and roads connecting them, but we also have some number. It might be the distance between them, it might be the time taken to travel, it might be the cost of traveling between the two towns, who knows. Whatever it is, that is what we mean by the weight of a network. And so the shortest path will be the journey between those two towns, which has the smallest total value. There are various ways of approaching the problem. You could just do it by what we call by inspection, where you just look and find the shortest path and hope that you are correct. Or more professionally, you need some kind of what is called an algorithm, which is a way of not only working out which is the shortest path, but also of proving that all the other options are longer. There are two algorithms mentioned in this presentation. One of them is the one in the textbook by a gentleman called Dijkstra, and the other one was devised by me about 2 or 3 years ago because nobody found Dijkstra's algorithm in the least bit easy to use. First of all, by inspection. So what is the shortest path from, say, town C to town F? Now, it wouldn't take you long to work out that if you go to B, that's 5, down to E, that's another 4, making a total of 9, and then up to F plus 7 equals 16. It probably doesn't take much addition to work out that any other way of doing this journey is a bit longer. So that's by inspection, which is a perfectly valid way of solving a problem. It would work on a very small network like this one. I don't think it would work on a larger one. There's a picture of Dijkstra, and there is the couple of the pages of his solution as printed in the textbook to the same problem. Now you can see that there's a lot of work there, and I haven't tried to reproduce it in detail. There are actually more pages of his method just for that question than are given here, and it has over the years defeated teachers and students who are trying to make good use of this algorithm. So we don't want you to look at it unless you particularly want to. We're offering you Allen's algorithm in its place. This is how it works. I suggest that you have a piece of paper while you listen to this recording and try and reproduce what I'm doing. I may not finish it, but you might like to finish it after I've started. So the shortest path from C to F. We're starting at C, so we make a little mark of point C. And we look at all the ways that you can go starting at C. Now, starting at C, you can either go to B and D. Now, we're going to make a sort of tree diagram, so you need to spread out initially the nodes so that you've got room to make more tight nodes underneath. So C goes to B, and C goes to D. C goes to B is 5 and C goes to D is 6. Now, taking those two in turn, B and D, where can you go from B? Apart from going back to C, which is no purpose to that, you can go to A and E and D next. So under there, A, E and D. From D you can go to B, A and E. B, A, and E. Now the numbers you put on there are not the individual numbers. You add up as you go. So CBA is 5 plus 7, which is 12. CBE is another 4 onto your 5, which makes 9. And CBD is another 5 on the 5, which makes 10. Similarly over here, D to B is 5, so that's 11. D to A is 8, so that's 14. D to E is 9, so we got 9 and 6 is 15. Now we're going to F. Now we don't want to make too much hard work for ourselves. How do we get to F from one of these? Now from E we know that we can get to F, which is 7. E to F is 7, so 7 plus 9 is 16, and we've got there, so we can put a line under there to say we've arrived. Now the point is we found a 16. Any of these journeys which are longer, going to be longer than the 16, we can discount them because we're trying to find the shortest path. But we haven't found any more than 16 yet, so we have to keep going. From A, having got there so far, we can go to F, which is 6, but that's an 18, so that is too long, so we can cross that one out. From A, we could also go back down to D, which is going to be too long as well, so we can cross that one out. You're perfectly justified in crossing it out. From BD we could go to A or E. Going to A is going to take us to 17, so we can cross that one out because that's too much, and so on. You've got to produce evidence that you tried all the others. So C, B, D, E is going to be too many, that's 19. So we can cross that out. And it looks like our 16 is the candidate. What about over here? C, D, B. We have to go down to E, which is another 4. That's already 15. C, D, A. We have to go to F, which is 6. But that's 20 altogether, so we can cancel that one out. This one's going to be too much because we've already got to 16. We can cross that out safely. And this one as well, it's already 15, so we can cross it out. Which proves not just that the shortest path is 16, but also all the other paths are longer. And that is the essentials of Allen's algorithm. That is the drawing that I did last year. Much the same kind of thing. So you can make the choice whether you use Allen's algorithm or Dijkstra's algorithm. No pressure. Let's have another one. Shortest path from A to F. Alright. I'm going to do it here, and then if you would like to try and do it first before I do it, then you can check your answer afterwards. So pause my presentation, and then when you've had a go, have a look and see whether I've done it the same way. Going from A to F, so A at the top, B and C. After B we can go E and D. A, C, we can go B and D. You can do these things first if you like. A, B, E takes you to F. A, B, D will then go E and D, and then F. We can put the numbers on later. A, B, D, you can go to E, then F. We can go back to C. A, C, B, we can go E or D. You might find it easier if you do all the heads first and then put the numbers in afterwards. A, C, B, E, we can go to D or F. A, C, B, D, you can go E or F. A, C, D, E or F. So those are all the possible routes that we can take. Now put some numbers on them. A to B, 2. A to C, 6. B to E, 2 makes 4. B to D is 3, makes 5. C to B is 2, makes 8. C to D is 1, makes 7. E to F is 3, makes 7. E to D is 2, makes 6. And D to F is 5, makes 11. So that's out because we've already got a 7 there. D to E, 2 makes 7. This is going to be more, so you can cross that one out. This is already more than 7, so we can cross out all of that lot. And this is going to be more than 7, so we can cross that out. So there's your answer, A, B, E, F. And that's it. And there is your success criteria. You can use one of the algorithms to find the shortest path on a network and prove that all the other paths are longer. If you want to do more, which will be good for you, because this is definitely going to be in the exam, then 6G is on pages 245 to 248, all questions. Thank you.